So it's my pleasure first to introduce the chairman of the session, Air Vice Marshal Ravi Burli VM was commissioned in the flying branch as a flight pilot in 1976. He is a graduate of National Defence Academy 1975 and Royal Air Force Staff College, Bracknell, UK in 87-88. During his career spanning over 3 decades, he has flown several types of fighter aircraft with 4,300 hours of flying experience, a fairly large quantum of which has been maritime attack operations on the Jaguar with 6 Squadron Air Force Station. He is also an A2 qualified flying instrument rating instructor, an examiner and a flight strike leader. He has commanded a Jaguar squadron and has been on the directing staff of Tactics and Air Combat Development Establishment, TACD, and Flying Instructor School. He commanded TACD from February 2001 to November 2002. AVM Burle has been the leader of the IAF Observer Group to Alaska for US Air Force multinational exercise Cope Thunder in 2000. During the staff and command tenure of TACD, he has been intimately involved in several developmental and operational air power trials at the IAF level. Also, he has been on the directing staff of Air Wing DSSC for 3 years. He has been the Chief Operations Officer at Air Force Station Jamnagar and overseen extensive air support operations during the Gujarat earthquake of 2000. He has commanded Air Force Station Hasimara from July 2007 to May 2009. He has been the defense attaché to Sweden with accreditation to the 3 other Scandinavian countries of Denmark, Norway and Finland. He has been commanded twice by the Air Chief of the Air Staff in 1991 and 1995 and awarded the Vayu Sena Medal in 2000. Now presently he is the Director, LC Induction at ADA, Bangalore since 1st December 2010. Now I hand over the session to AVM Murli sir.
Thank you. Ladies and gentlemen, it gives me great pleasure to invite you all here for the session following the plenary session on the aircraft technology evolution. And we heard some very fine presentations during that immediately preceding session that we've just been through. And now, of course, as was told you earlier, we are divided into 3 technical sessions. And this is the session 2A and it pertains to flight testing. We have, as in all the sessions, 4 presentations. If the previous session was a little bit of a nodding the head kind because it is immediately succeeding a fairly sumptuous lunch, then I must say that this must be the keep awake session because if we just had tea, and I think we would be, if we go by the normal physiology, in a more receptive state of mind. But at the same time, it shouldn't become too long because then we'll probably go into the naughty session just preceding bedtime. So I will now start this session by inviting the first speaker, a few words about the topic and about the individual. The first topic is upgrading propulsion systems on the C-130 and C-5 aircraft from a test pilot's perspective. And we have Mr. Wayne Roberts, Chief Test Pilot, Airlift Program, Lockheed Martin Aerospace, who is going to be speaking to us about this. Basically, it'll be something to do with the C-130J being a major upgrade, as we do understand, of the C-130 aircraft. The main upgrade portion, of course, is the Rolls-Royce AE 2100 turboprop engine, which is, of course, among other technicalities, computer controlled. It also has a unique 6-blade composite prop with 20% enhanced thrust. And of course, there's the inevitable requirement to keep costs low, other aspects remaining the same, and this meant to them longitudinal, lateral, and directional handling qualities change because the airflow over the surfaces changes for a more powerful and rapidly revolving propeller, as it were. And of course, here to keep the costs under check, test pilots played a lead role in identifying differences and providing innovative solutions. Same thing with the C5, not exactly in the same vein, but in a similar kind of direction. Re-engine to provide 25% enhanced thrust. It encountered, I'm sure, similar challenges, no, not the same challenges, similar challenges. And again, test pilots played a pivotal role to find cost-effective solutions. Mr. Wayne Roberts, eminently qualified to speak from his CV. It is quite apparent on this subject. A BS in Mechanical Engineering from the Polytechnic Institute, 1977. Federal Aviation Administration designated engineering representative, Lockheed Martin Fellow. Of course, he has had illustrious career in the United States Navy. Indeed, he's a retired captain of from the United States Navy. 12 years active service, 11 years in the reserve. He is, other than being a P3 pilot with extensive operational experience all over the world, he is also a test pilot from the class of 87, a lead multi-engine instructor test pilot in the test pilot school of the United States Navy, a Navy test pilot for classified test programs, and I'm sure he's going to be speaking a lot about that today. Are you? No, okay. So without further ado, we can look forward to a very fine presentation from him, I'm sure. So it's over to you, Mr. Wayne Roberts.
Thank you very much for that kind introduction. It certainly is a pleasure and honor to be here in this very distinguished group. It's my first time to India, and this is my second day, so it's certainly a great opportunity to be here. I am from Marietta, Georgia, the plant that builds the C-130. It's been in production since 1954. It designed and built the first jet transport, the 141. It designed and built all the C-5s, the largest transport for the U.S. military. We just finished an engine test program in the C-5. The C-5s will probably be flying for 70 years. First business jet was designed in Marietta, the Jetstar, and the F-22 production is in Marietta, the first fifth-generation fighter, and we're going to be manufacturing major components of the F-35. So, pretty exciting place. Very, very fortunate to be there. I'm here on the occasion of the delivery of the first C-130J to the India Air Force. The India crews flew it over last week, and they were inducted. The airplane was inducted into the Air Force on Saturday. It's now down at the show. I've had a great opportunity to start working with the India pilots who have been in Marietta. It's one of the best parts of my job is to work with the customer pilots. We kind of live vicariously through them. They use our airplanes in ways that we only wish we could. They ask incredibly good questions, some of them about very hot conditions, which I really didn't know much about India, but I'm very glad that I'm here in Bangalore in February, I think. And also high altitude operations, higher than I would have imagined as well. And I think the C-130J will be very happy in this country. It is those are two areas where the C-130J really excels very well. I'm going to start the presentation with this slide. What's on here is kind of one of our customers' results, and a lot of times our competition is our old C-130 since we've sold them to 67 countries. Turn here if you can still hear me okay. This is a typical mission that the U.S. Air Force was flying out of Kuwait. Has about 6 stops and come back. Basically, the C-130J would do that in one day, load up, full cargo, full fuel, hot day, and do this mission. Their older airplanes took 3 airplanes to do the same mission. We see this over and over again, and I want to talk a little bit about this multiple, because that's where the airplane makes all the difference. First, small things, I'll get them out of the way. We think of them as important, but digital control throughout the entire airplane. Everything is digitally controlled. Even the gear goes up through mission computers. We certified digital circuit breakers. I'm going to mention FAA quite a bit because we actually, in our test program, we used the FAA to certify our airplane. We had just the RAF and the RAAF as our customers, and we needed a good certification base. And we certified head-up display as a primary flight display. The cargo compartment's all electronic, very easy to convert. So on this mission, if you had rolling stock or cargo that comes on in pallets, or you have to reconfigure for troops, all that gets done very quickly, computer controlled, and also doing all the weight and balance, those kinds of things. Great time navigation, etc. But those don't make this multiple. What makes this multiple is a lot more thrust. And I already mentioned in the brief that it's we picked at the time the best turboprop on the market, the first integrated computer-controlled prop and engine, but a lot more thrust. But we did want to make this airplane affordable and take advantage of our place in the market with what we learned in 50 years. And that decision was to not make major changes to the flight controls or the aircraft frame. We've fine-tuned both of those. We know exactly what's going to wear, when it's going to wear. We've replaced all the parts with better components. And if you've how often do you know a component that's been fine-tuned for 50 years? There's nothing really much more to learn unless we start changing it. So that was the place we chose to save money. But we had a big challenge, and that was to handle all this thrust that the rudder, ailerons, flight controls were not designed for. I'm going to concentrate on that. It was a very interesting flight test to go through that event. Obviously, the answer is already out here because the airplane's been in service for about 1 million hours now, delivered 200 airplanes, but I'll tell you a little bit about how we got there. First, I want to talk about turboprops for a moment. I get a question about once a month that says, why do you still have a turboprop on there? I thought we started replacing them all the jets back in about the 60s. And there's a great answer. Turboprops produce more thrust, far more thrust, from 0 to 150 knots than any turbofan ever could because of the way the blade angle changes. And you take that, put it in front of the wing, blow it over the wing, 20 knots. We get about 20 knots of equivalent airflow from the turboprop blowing over the wing. So if I could rotate at 80 knots without the power, I can rotate at 60 knots with it. But there's some things that are difficult. All that prop wash is vibration, goes to the airframe. Again, we know all that because we've been working on it for 50 years. Not a coincidence that we had a 3-bladed prop in the original design, and we have a 6-bladed prop now. The harmonics are the same. The other piece of it is the flight control, is the airflow swirls around and pretty much blankets the airplane in a very complex way. At the end, I'll show a little bit of video where we captured a little bit of that interesting flow pattern. So those are the challenges. I think you'll agree Airbus chose to meet every one of those challenges with A400M because they recognized that the performance benefits of a turboprop. Okay, so the challenges, what I'm going to try to do here is take you through about 4 or 5 things that happened. Some of them we didn't expect because we really couldn't model all that prop wash. First one, before first flight, we were doing a single-engine demonstrator, and we wanted to see how it would work. This particular thing that I'm going to talk about has to do with the ground range. In this particular case, we're going to be pulling the power lever back, and we're looking at the blade angle here. And we want nice linear thrust, of course. The wings nice and long, fuselage gear very close so we can taxi on roads, but it makes it a little bit rolly on the ground. And so if you have asymmetric thrust or any kind of a thrust nonlinearity, you're not going to like it. And sure enough, this is basically what we got. Flight idle, ground idle. Below 100 knots, this is what you're going to have. That's the minimum blade angle at 100 knots. Above 100 knots, you're going to be up here a little bit. But we hope to come back down here. But let me show you what we actually got. Those yellow lines, if we were to come in at the higher speeds, they came straight across, and believe it or not, straight down. About 6,000 pounds of thrust change when the power lever got to ground idle. Now, you got to say, how the heck did it happen? Well, we really brought it on ourselves. we gave Dowty a requirement to maintain very, very tight RPM controls to control our AC generator frequency. And what's really behind this? Why did they have to do this? Props and windmills are the same thing. It's just a function of blade angle. We have to go through the windmilling range at the high speeds. And it wasn't a problem in the old engine because the old engine was connected to the compressor. Compressor is a tremendous prop brake. Now we get better fuel economy by splitting those apart, but the prop now doesn't have much resistance and the overspeed problem. Okay, now we're about ready to go to first flight here, and we have a major control problem that we have to resolve. First thing we did was we backed off on that requirement for AC generator. The avionics didn't mind much. We changed the GCO control and gave it Dowty a lot more room to work. But I knew what I wanted for flight controls and handling qualities. Dowty knew how, what they could do. I can't give you any details. They did a superb job. It's proprietary, but in general, we got something pretty close to what we want, almost this. Didn't know in first flight, we did some taxiing. It looked pretty good, but it wasn't until the end of the program. I did about 5 two-engine out landings, and we actually have to manage thrust and use that thrust in this high-speed range to control the airplane with 2 engines out on one side, no nose wheel steering. And so at the end of the program, to have proof that what we did before first flight worked real well was really neat. So that's one problem out of the way. Just a convenient picture here. I do the air shows in the C-130J, and I think this was taken at Farnborough by somebody. I'm not sure how the sun shines up into the sky like that exactly, but it's haven't quite figured out how that was taken based on the sun angles. But okay, the next major thing that isn't a surprise is VMC. We put a lot more thrust in the airplane. We didn't increase the rudder. Obviously, you lose an engine, and the asymmetric thrust is going to yaw you. The pilot steps on the rudder, tries to balance that. Now, the key is that, as long as you can balance it, you're okay. But we talked about the fact an awful lot more thrust. As you slow down, the thrust goes up a lot. As you slow down, the rudder moment goes down. So there's a speed, it's called minimum control speed, where those are matched. The speed goes way up when we have this thrust. Everybody else would probably have made a bigger tail at a huge expense. We had a digital system, both in the engine and the mission computer, and we came up with an idea which sounded ridiculous, but let me play it through. If we were to pull back the other engine very quickly, we could control VMC anywhere we wanted it and still have the other 2 engines at full power. So that was a technique we started looking at. Have to be able to do it very quickly. Looked like we could do it. Rolls-Royce had a great torque limiter that we decided would just control, that could run that torque down in a half a second and keep up with a failing engine. If you're late bringing the thrust back on the runway, the airplane deviates. It's over. It's like stepping on the brakes after you hit a wall. It's of no good. So that was important. The other really big risk was the FAA. The FAA really doesn't like to take on big new challenges, and they really did almost fight us on this. All right, nobody had done it before. We had to figure out how we're going to do this. Obviously, 100% power. We can pick this minimum floor over here. This is basically what we're going to do with a good engine, bring it back. We don't need VMCG less than about 70 knots. It will have no effect below 70 knots, so no sense in pulling it back any further. So we dial in the number we want, about 60% floor here. All that's left is to figure out that slope. Well, as you're slowing down, we're going to add rudder. Before we get out of rudder, we're going to slide down the slope. Why not do it at constant rudder force? Wasn't the original thought, but it turns out we decouple pitch changes on that ramp with lateral directional control changes. We use the engines to basically completely decouple. You change speed, you do not change ailerons or rudder. So we actually made the handling qualities much better because we had to put a ramp in there. Anyway, so we did it, and we had to do this all in flight test. There wasn't a lot of good simulation of all this prop wash and so forth, so all of this was done on the runway. We had orange software. We could control all these things. That was really great. A very flexible test program, and it was a neat place to be. Now the question is, was it a dumb idea based on performance to pull back the second engine? I'll give you 2 test cases. Okay, what this is kind of like summing up, if you will, the 4 engines. A power here. If you lose one and you pull back some, then you're going to end up with like 2.6 engines at the worst case. This first one's a lightweight case at standard AC level. pull back. That's the slope we saw before where we restore rotations here, obstacle clearances here. By the time we get to obstacle clearance speed, and on 3-engine power, this is 40% of one engine, but it's only about 13% of your 3 engines. Here we're down to about 5% power loss. And the airplane's super light, and it's standard day. We don't need it. So it doesn't hurt the lightweight case. We've overpowered the airplane anyway. Heavyweight case, minimum speed will have to keep going. The critical engine failure speed's way up here. This is heavyweight, but standard day. Still not a stressing condition for the airplane. And right after rotate, this is about 2 seconds acceleration. No measurable performance penalty, and we're still at standard day. I said that we're going to keep this constant rudder force, this slope. If we add density altitude, this slope goes left. Add 10 knots or 10 degrees centigrade above standard day, 0 penalty at sea level. You add 1,000 feet at standard day in terms of field altitude, 0 penalty. And of course, everything hotter and higher, ATCS is 0 penalty. So it really almost is, you almost can't tell that you've got an ATCS system when it comes to performance. All right, so what does that mean in the C-130J application? We have 2 lengths of the airplane, short. In the short airplane, the rudder's not so far back, so VMC is more of a problem. When we were doing our VMC testing, we could not measure VMCG in the short airplane. We get up to 80% power on the outboards. If we went any higher and failed an engine, the airplane was in the air, essentially flying speeds, before we found it. The rudder's starting to get blown back. The airplane is so overpowered, we couldn't even test it with ATCS off. FA rules, ATCS on, that's the field performance. That's critical field length for standard day. Military rules, which we use nose wheel steering and take credit for that power to lift, that's critical field length. Long airplane, we actually could fly the long airplane without ATCS, but kind of a ridiculous looking critical field length. Similar FA rules and military rules. And to summarize, there's long and short to military rules, which our customers, we hope, are using every day. 4,000-foot runway, max gross weight on both airplanes. 3,000-foot runway, about 2/3 gross weight. And almost half gross weight on 2,000-foot runways. And we started with an unflyable short airplane and a kind of ridiculous long airplane. We did this because we needed to, but this tells me that every airplane, with every 4-engine airplane that's flying in the world today, at least a turboprop where you can pull power back quickly, has way too big a tail. And I believe that we're going to see that. I mean, I don't get to hear everything, but we're going to see this system on other airplanes. So sometimes when you're in a jam, you do something, and I don't think we didn't realize what we had until a lot later. Just real quickly, I'll show you in the cockpit. We had to design the cockpit stuff for the the pilot. It's quiet. It does its job. Pilots find it really easy to fly, so they accept it very much. But just to give you a quick idea here, rolling down the runway, V1's going to come up right here. The engine's going to fail just before V1. Number 1 fails. Number 4 pulls back, and as you accelerate, number 4 comes back automatically. Again, at that perfect co-pilot power setting rate that you just hold constant rudder. It really feels neat the first time we did it, running down the runway, and this power comes up. You hold what you got, and you just feel this acceleration come back, and the handling quality's just got better, so kind of neat. Okay, that worked out extremely well. We're doing the first engine out landing, and we have another problem, not predicted. Oops, get out of here. Okay, engine out landing, now the prop is pulling backwards. Number 4 is out, it yaws in the direction of the good engine. At about 90 knots, think about the fact that these inboard engines now, they're pulling you backwards, but they do it by disturbing all the air in front by this big, if you will, disturb air in front. We think the tail was flying through it worse than it was on the old airplanes. And by about 90 knots, the tail wasn't doing anything. It was in dead air as it was flying through that inboard prop wash. Now this engine's pulling us back too far. All right, we're really late in the program. We're trying to do field performance, and we don't have an airplane that can stop with an engine out. The FAA requires you to stop with an engine out with no nose wheel steering on a dry runway. We had a small test team, just finished ATCS development out at Edwards. We basically got an FTDR, a flight test request signed that said, see if you can find a fix. Very quick test plans. We knew we needed to, we didn't have enough rudder. We knew we needed to reduce the number 4. We couldn't do an ATCS system. It didn't make any sense with a mission computer. This is a ground idle case. It's not a torque case. We need to move the ground idle blade angle. The FADAC can't do that dynamically, but we could change the FADAC software and do it all the time. We chose that. All we needed to do now is pick a schedule. We actually used stops. We cut at night in the shop so we could move the power lever back, and it would stop the power lever in different blade angles. So as I was flying, I could slam it back into this metal stop and get the blade angles we wanted. As a sort of make-do ground idle detent, if you will. What we really had was that was the original schedule now. This is 1 degree blade angle, which is where the original schedule was as a function of speed. And basically at 90 knots with number 1 engine out, this was too much reverse thrust on number 4, so we want this line to go up for the outboard engines. We came up with something like this. And the inboard engines we programmed in a little bit. Now the inboard and outboard engines do about the same thing. We sorted this out in about 2 or 3 weeks. Tested it in crosswinds, got orange software so we could actually make this happen, programmed it in FADAC. In about a month and a half, problem was solved, tested with new software. Again, pretty neat to be part of that. Okay, we've seen this diagram, but now I'm going to superimpose what I just told you, because now I'm talking about the ground idle detents where that happens, and it looks something like this. The outboard engines start in the same place, and now they have program up at the higher speeds, to higher blade angle. The inboard engines will program back the other way down here. Notice straight lines between everything. Software is a wonderful thing. You create straight lines, you move the endpoints, but the straight lines are always being calculated. The pilot never notices that the endpoints are moving. He's got linear thrust all the time, much more linear than the original engines, which the original engines always had to come down from here and jump down to the gate. So just by using software, all those problems, which could have been solved with a bigger rudder, were solved this way. And of course, the taxi speed, the orange line, when you get back to taxi speed, we're back on where we want to be. Main metering valve problem. I didn't know about this very early. I'm not sure who else did. But the problem is, on a FADAC engine, it's one fuel valve controlled by a little milliamps out of the software that says more gas, less gas. It's about the only moving part. But that little metering valve can stick, theoretically. Very low probability, but theoretically it can stick. If it sticks to full fuel flow, the prop works real fast. That's not always a good thing. It'll absorb that energy and give you a huge overspike in torque in about a half second. If we're on the runway and landing when this happens, it takes us off the runway. Single point failure, FAA doesn't allow it, no matter how rare. They told us we had to fix it. Everybody else with turbofan engines were getting around the problem, I think, because they didn't react as quickly. So this one ended up hurting us. They were giving us no choice. Rolls-Royce and all the engine manufacturers said they can't solve it at the time anyway because they couldn't react fast enough. We needed them to react very quickly, and they'd false alert too many times because they didn't know exactly what their engines were going to do. We came up with an algorithm that compares all 4 engines because we had 3 engines that were perfect models in the same condition as the bad engine all the time. So just by comparing the engines, we're able to look for the bad engine without ever having to predict what a model of an engine was because we used the 3 engines that were there as the model. So as soon as the engine kicks out, we shut it down. FAA was happy. This only took 3 or 4 weeks to write the software, not a particularly difficult code. We wrote all the software in Marietta, and we turned this stuff around very quickly. So again, that was pretty neat. Okay, one last thing, destabilizing thrust. This is just a fact of propellers when you mount them in front of the CG. I was researching this a little bit, and I was told that the Wright brothers understood this, so I figured it was about time I did. If you look at the flow flowing into the prop, just the airflow, that's basically, we'll look for side slip here. We step on the rudder, we generate a side slip. But take a look, what does a side slip do? It actually, because we're actually changing the momentum and the direction of the flow, we're kicking a little bit of a normal load here. We're creating a yawing moment, which is in the same direction that the pilot applied the rudder, so it's destabilizing. I put a little rudder in, and I get help. okay, we don't have a big problem, small part of the envelope where we can get rudder overbalance and rudder lock. It's at high power because we're destabilized, gear up, 50 flaps, very slow speed. C-130's always had this issue. It's never really been a safety issue, but we were making it worse. FAA doesn't let you make things worse. So we had to come up with something. We didn't come up with any clever fixes to change the physics or prove the Wright brothers wrong, but what we did instead, by the way, one other thing before I go to that, this is the rudder lock condition, if you don't know what it is. We can generate so much side slip at low speeds that we can actually get the side slip beyond the rudder and blows the rudder to the stop. The FAA was very interested in this as well. We basically had ignored this in the early days of the C-130, knew the rudder lock was there, stayed away from it. But the FAA wanted us to test it. Again, great place to be. We tested all the overbalance in the entire envelope, and it was mapped it up for the first time. We actually ended up doing an awful lot more tests on the C-130. 50 years of operation, we learned probably twice as much as we had known before. And what we decided to do was just alert the pilot. We already had differential pedostatics that told us side slip. We use it for various things, so we just decided to present the side slip to the pilot with a side slip alerting system. Head-up display. The triangle is side force. We created a new symbol, the rectangle breaking off from the triangle. The difference between those two is the side slip. We put up a side slip fence when it gets close to the limit. The limit varies for different configurations of the airplane, gear up, gear down, high power, low power, engine out, ice on the tail. But it doesn't make any difference. It's just a limit. So as far as the pilot concerns, the limit comes up the same place. You don't hear it now, but there's an oral alert for side slip. And the side slip's displayed to the right. You step on the right pedal just as you would for the ball, so all the sense is the right. Also, because we're displaying side slip, for those of you that are, multi-engine pilots, you want to fly zero side slip with an engine out, but with a ball out. All you got to do is make sure this home plate right there is set, and you'll be flying zero side slip. Again, an added benefit that wasn't really there. It wasn't necessary, but we took advantage of it. Okay, that was sort of a quick overview. I think I'm doing pretty good on my time. I want to talk a little bit about, by the way, not that exciting, but we ended up having to put a stick pusher on the airplane, and we ended up taking an awful lot of video stalls. We put 5 cameras in the tail, and back then, when we did the debrief, we'd put the 5 TVs up. Since then, we've been able to put them together. The only reason I'm going to show this to you is it captured on this stall, and we have probably about 1,000 of these stalls, but the wing's all tufted. You can't see it in the video, but we're going to fly through some moisture, and you're going to start to see these flow patterns come off the prop. And we were able to see the tufts. You won't be able to see that detail, but the tufts being affected by these flow patterns, and that's what caused the roll-off of the stall. We didn't have the roll-off in the old props, and we did on the new. It was just the way the props changed the flow pattern asymmetrically across the top of the wing. But you can imagine the same kind of thing. You're starting to get some of that vapor here. This isn't very distinctive. In a little while, we're going to see a little bit of another pattern that just shows up real well. Let's see if I can stop it here. Starting to see some of that pattern. Those are the vortex coming off the wing tips, the prop tips, if you will. And you can see it's very asymmetric. It's all shifted to the right. Interesting patterns. And with the tufts, you could see how the tufts were affected asymmetrically. But imagine all that's flowing across your rudder as well. Just quite a bit to deal with. Pretty neat. Okay. Just want to summarize a couple of lessons learned. This program was a commercial program. We tried to convince the U.S. government to fund it. They weren't interested, but we believed if we built it, people would buy it. We had customers that were interested in doing the new propulsion system, the Brits and the Australians and then the Italians. And so we decided to develop it as a commercial program on Lockheed's money. Certified with the FAA. A lot of risk for getting your money back, but the advantages to us on the program were we made the decisions. We had a very, very compact management structure. When we found a problem, the people that understood the problem went after fixing it. I remember getting almost no direction because we knew what we needed to do better than anybody else. We told them what money we needed, what time we needed. They figured out the money. And every one of these problems, the people that knew the most about it had given full authority to work it. We didn't have to go back and give 3 choices. We didn't have to go brief somebody that knew nothing what was going on. And we didn't have to go work through multiple management layers with different, for example, if we had a big customer. The FAA is standoff until you're ready. Like we had customer pilots with us all the way through, the RAF, RAAF, the Italians, and later on the Marines and the Air Force. We were able to work with them, but they didn't make the decisions. So a lesson learned was that, I wish more programs could be that way. It certainly, I think, saved us a lot of time. Having worked on many other programs since, where you get your test plans approved 2 years in advance, and everybody's afraid to go ask for a change. You got to ask somebody that doesn't know anything about it because he signed it. Anyways, very refreshing. I'm not sure I'll ever see another program like that. That's it. Hopefully I gave you a little bit of a feel. We certainly hope the C-130 supports India, and I look forward to coming, hearing the good questions and helping out. Any questions?
Thank you, Mr. Wayne Roberts, for a very objective presentation on basically innovations born in test pilots and test engineers' minds that could make solutions of get us solutions in terms of re-engineering legacy aircraft in the manner that you have just told us, without any extensive recourse to structural changes, system changes, etc. I'm sure there'll be a number of people who would want to speak to you in greater detail on this subject. Unfortunately, I think we've all understood that we are not really structured to take effectively questions and get into any kind of discussion at a forum like this, because there are 4 groups. But I'm sure in the coming period, including the time that we spend perhaps, and you are going to be part of that Aero India exhibition as well as the displays commencing tomorrow, people will take the opportunity to use this to further enhance their knowledge on what you have had to say today. So thank you very much, and also very heartening to note that you feel that the high altitude operations, which is going to be pretty routine for the Indian Air Force, the C-130J is going to be at home at those heights. And from what you have said, I'm sure that is going to be the case. So thank you very much once again.